All right, so we started doing second order circuits with constant sources. Constant sources meaning DC sources, right? So I kind of talked about this a little bit the other day, right? These guys happen all the time when I have switches. And the example I gave here is I said this guy is what I would call a photovoltaic inverter, right? So it's basically if I had a solar panel on the DC side and I was connecting it to the grid. All right, so those things over there are transistors, they act like switches. And these things here, the voltage on the top and the current on the bottom, these are actually the voltage across one of those switches and the current through it. What that shows is a second order response. If I have a second order response, right, what does that mean? How many energy sources do I have? Two. Typically one of them is an L and one of them is a C, right? It could be two L's, it could be two C's, but usually it's an L and a C. And in this case, I said, the ideal scenario would be I don't know if it's an ideal scenario, but if I had just a purely LC system, just an L and a C, I call that an undamped system, right? If I have an undamped system, there's no what in that system, we said the other day. No losses, no resistance, right? So basically what would happen in that LC circuit, I would get basically just a pure oscillation. The voltage would basically just be a pure sinusoid. And you would see that the current would be a pure sinusoid. This response that I see right here, what is that? What do we term that? Underdamped, right? So he starts out like a sine wave, but what I see is that his sine wave decays over time. Now, one of the things I want to point out here is we talk a lot about transient and steady state. This is really what I see when I have, this is very typical, this circuit here is what I call power electronic circuit. Very typical of what I would see in systems where I have these kind of LC second order responses. I see a switch changed here, somewhere in that circuit, a switch changed. And then I have a transient and a steady state response. And then basically the switch changed again, right? And there was a new steady state. Where's the transient here and where's the steady state? When you flip the switch. The transient is when I flip the switch, and the transient is this piece right here, this oscillation whose amplitude is decaying. Right? When I get out here, there's not really any oscillation left. That's the steady state response. Okay. Out here is the steady state response, and then essentially the switch is moved, and then I transition to a new steady state. And the transient is basically, just the pathway that the elements are taking to get to that new steady state. All right. So this is a sort of general idea of what we would see. All right, and those kinds of power circuits, we tend to see a lot of that sort of stuff. All right, so the other day I laid out a 6-step process for these things. All right, and we're going to go through some examples today, but a 6-step process, which really isn't all that much different than what we would do with a first order circuit. Right? We basically got to get the differential equation, solve it. So when I say x of infinity plus x transient, so first of all, what is x? In one of these circuits, what's x always going to be? Capacitor voltage or inductor current. X of t is always going to be either capacitor voltage or inductor current. Why those two things? Well, those are the energy storage quantities, right? I is related to the energy storage in the inductor. V is related to the energy storage in the capacitor. You're never going to see anything for VL or IC. Okay. You're going to see them always for IL or VC. Basically, the energy storage variables are the ones you're going to see. All right. So what's this? So solve it. X infinity plus X transient. What's X infinity? What's the term we use for that? Steady state. That's my steady state solution, right? And my step 3 is to find the steady state values. All right. So how do I find the steady state values? What simplifications do I have to make in the circuit? Capacitor becomes an open, inductor becomes a short. Okay. Make sure you know that. You need to know that for the test for sure. There's going to be at least one first order on that test. Okay. Now, fourth part here is basically to get the initial condition. And I analyze the circuit at t equals 0 minus. What's it mean to say analyze it at t equals 0 minus? What's that? Before the switch moves, right? So before the switch moves, and what we say is that the capacitor voltage and the inductor current are the same right before and right after the switch moves. Okay, now, if I have a second order differential equation, I need two initial conditions, right? What's the other initial condition that I always need? Well, what value, we will solve for it right after the switch moves, but what value do I, just in general in a math context, right? If I have a second order, I always need two differential or two solutions, right? Two initial conditions. The derivative. I need one for x of 0, and I need one for dx by dt of 0. And specifically, again, what we never talk about at 0, and the reason we never talk about at 0 is because the switch is in motion at that point, and mathematically everything's kind of undefined. So what we do is we look at the circuit at t equals 0 plus, which means specifically right after the switch moves. So here, this is before the switch moves, this is after the switch moves. And we solve for whichever one matters, dvc dt or dIL by dt. And then we put them all together to get the final total solution, which is going to look something like whatever that looks like there. Okay. All right. That's our process. I went through the other day. My standard form of the equation is that thing up there, that d squared x by dt squared. It always has a solution that is the steady state plus the transient. And the way we solve this thing is to get the transient solution, right? I said this the other day and I got some weird questions afterwards, right? What is the solution to any differential equation always? The transient solution to any differential equation is always what? If there's nothing that you know about differential equations, it's probably this. It's going to end up with an exponential. Always going to have an exponential. And if I have, in this case, a second order, I'm going to get two exponentials. If I had a 15th order differential equation, how many exponentials would I have? 15. All right. Now, the weird thing is, they can become sinusoidal. All right. And that was something, how that can happen, why that happens that way is something that you'll see with Dr. Yawu in 2254. But basically, we guess that the transient solution is a e to the st with a not equal to 0. You put that into what we call the homogeneous equation, meaning you set the equation equal to 0, and you get this polynomial. That polynomial has two roots, right? How do we know that has two roots? Well, it's quadratic, right? And so we end up with this formula here. Now, what I have done here is basically, I've kind of created a formula here that says, all right, there's two terms in here. There's alpha and omega naught. Yeah. If I take the square root of some number, everything's fine and good if that's the thing I'm taking the square root of is what? Positive. But if it's anything that is not positive, if it's negative or 0, I have some weird situations, particularly if it's negative. What's that mean? Square root of a negative number is what? Imaginary. All right. And so if it becomes imaginary, the key thing defining that for us is this alpha and omega naught, right? And so we define some conditions and we define our solutions based on those. So I said this the other day, if alpha is less than omega naught, right? That's the case where this guy is underdamped. Okay. Yeah, you can get all these formulas in the notes. Don't worry about writing these down, right? Basically, this guy here is where I have a decaying sinusoid. And you kind of see a decaying sinusoid. It's a sine wave function. And its amplitude is decreasing over time because the amplitude's multiplied by an exponential who's getting smaller. Critically damped, as I said, that's the weird kind of stupid case that mathematicians talk about, but doesn't really happen so much in engineering in the real world, is where the two roots are the same. In other words, if alpha and omega naught were exactly equal to each other, we would have this result. Overdamped is this one, where it's just purely two exponentials. In this case, the roots are always what? The two roots, it looks like a bunch of Greek stuff, but what kind of numbers are they? Well, so yeah, so the value over here is gonna be positive. The roots are gonna be real, right? Basically what we get is here the roots are real and different. Here the roots are real and the same. Here the roots are real and, the roots are complex. Right, so it goes from complex at the top for it's underdamped to real and the same to real and distinct. Okay, that's the basic idea. Now the other would be if it's undamped, which is the one that I talked about. There's truly no losses in the system. And the results, they change like this as I go from undamped to overdamped. Okay. Undamped, the transient response never goes away. All right, it just continues on forever. Transient response decays in a sinusoidal in the underdamped. And then critically damped and overdamped basically are just look like first order responses. All right, there's two exponentials that are decaying. Okay. So that's what the solutions are going to look like. And we're going to go through some examples of trying to find them. Now, the one thing that we know at the end of the day is for all of these things here, right? If I look at any of my x of t's, let's look at one of the simplest cases, right? If I had x of t, if it was overdamped, I have my steady state solution plus a1 e to the s1t plus a2 e to the s2t. And after you've gone through this thing, you'll know what S1 is, you'll know what S2 is, you'll know what X of infinity is. You'll know those numbers. What you won't know is A1 and A2, right? You have to solve for those. And you solve for those knowing X of 0 as a number and dx by dt of 0 as a number, all right? That'll give you two equations and two unknowns, and you can solve that, okay? All right. Now the form, so I give you in here, you would have to take the derivative of like x of t up there. And what is that x of t? Is ugly, right? You should be able to do that, but I have to do chain rule, or not chain rule, multiplicative rule to do that, right? It's ugly, it's messy, it's not fun. What I did here was I basically said, okay, well, if I had this and I took its derivative and I plugged in t equal to 0, it would simplify to that. All right, so you can use this later as sort of a guide for yourself to look at, all right, to see what the form looks like at x of 0. And we'll come back to it and use it in our examples. I have them for all of the cases. All right, now, every time I approach these, and we're going to look at this in some examples, again, you don't have to do it this way. You could solve it by hand in the homework and plug it right into the Canvas thing to solve it. You can do it the way I'm doing it here in MATLAB, which is to say you can have MATLAB solve for those things because there's two equations, two unknowns. I can use the matrix. You don't have to, all right, but you can, okay? And we'll do examples like that. All right, so now let's get into a real example so we can apply the process. So here's the circuit we're going to try. I got this circuit here and a t equal to 0. I'm going to close that switch. All right, and I've got L is 100 millihenries, R is 280 ohms, and C is 0.4 microfarads. And the thing I'm interested in is I want to figure out a differential equation for I sub L. All right, the inductor current. And I've been given, I don't have to solve for in this case, IL of 0 minus and VC of 0. I was given them. All right, so I was told that they were 0.1 amps and 10 volts. Okay. All right. So one thing real quick, what is IL of 0 plus? 0.1. Because IL is always continuous, VC is always continuous, right? So same thing with VC of 0 plus. If I wanted to know that, what is it? 10 volts. Okay. All right. So first step in my process is to find the differential equation. And I keep it general. I said X, but in this case, I want to do it for IL of T. Okay, so how do I do that? KVL. That's a good place to start. I got L, R, and C. And I'm going to close that switch at T equal to 0. Because I need to do it for the time period that the switch is closed. How much space did I leave myself? not enough. I'm going to go back here for a second. Before I get into this, what do I need to know? If I'm going to do a KVL, I gotta probably define a few things for myself. IL has been told to me is going that direction. And one question you guys always ask is, how do I know what polarities to use? You don't, and it doesn't matter, right? What polarity you use doesn't matter. You use any polarity you want, right? As long as you write down all the equations in a consistent way, use whatever polarity you want, right? What I'm doing here is I basically do it like this because I know that positive current would leave the terminal, the plus terminal, that 48-volt source. You don't have to, right? But I'm going to do it that way, right? I'm going to define these guys all like that: VL, VR, and VC. All right, so the thing I want to make sure that I remember to be able to do this properly is VL and VC and all that stuff. So how does VL relate to IL? Yep, LDIDT. Now, VR is equal to, how does that relate to what's going on here? Yep, IL times R. And what about the capacitor? How does its voltage and current relate? Yeah, so IC is equal to C dV dt. And what do I know about IL and IC here? What about the capacitor current and the inductor current? What do I know about them? IC and IL are the same. All right, because they're in series with each other. They have to be the same. Okay. Now, one thing, I always say, polarities don't matter. What would happen if I had written, let's say, V sub L with the opposite polarity? Let's say I wrote it like this, minus, plus. What would I have changed?
VL would just be negative.
Yeah, I would have VL equals minus L di by dt. Okay. All right, that's all it changes. So whatever polarity you write is fine as long as you write your equations consistent with whatever your polarities are. All right, you can do whatever you want. You're never wrong as long as you're consistent with your polarities. Okay. All right. So I'm going to keep it the way I had it. Okay. All right. Knowing all that, now I want to write, now I'm going to do my KVL. So I'm going to say 0 equals, and I always go around like this. Let's call this VL, call this VR, and VC I already did for whatever reason. Okay. So 0 equals, how do I do this? If I go around in a clockwise direction, first thing I do is I go through the 48-volt source. So how do I do my KVL?
48.
Be negative 48. If I'm going around in a clockwise, I go from minus to plus. Okay. And then I go plus to minus on the inductor. So that's plus VL. Then I go plus to minus on the resistor. And then I go plus to minus on the capacitor. All right, so I'm going to turn that into 48 equals VL plus VR plus VC. Now, we just wrote down, let's keep our eyes on the prize here. What am I trying to do? I'm trying to get a differential equation for IL. Does IL appear there anywhere? No. But how can I make it appear? How does VL, we just said, how does VL relate to IL? VL is L di dt. So I'm going to say this is L DIL by dt. That's putting in VL. How do I put in VR? IL times R. And V sub C, this is an annoying one here. How am I going to put in V sub C? Well, we said over on the other side, we said IL is equal to IC is equal to C dVC by dt. Right? Like that. So what I can say is that V sub C is equal to, well, let me just do it this way first. dVC dt is equal to 1 over C times IL. You guys with me on that? And then I can turn that into V sub C. How? Integrate both sides. V sub C is equal to 1 over C times the integral of IL dt. All right, and I can plug that in here. 1 over C times the integral of IL by dt. All right, now, is that a second order differential equation? Yeah, I don't know. I'm not sure whether it is or not by definition, but it's not in the form that we want it to be in, right? It's not, certainly not in our standard form. How do I get it there? How do I make it a second order differential equation in our standard form? Any thoughts? What can I do to it? I take the derivative of both sides, right? What if I take the derivative of the left side? What's the derivative d by dt of 48 volts? 0. Okay. The derivative of the other side with respect to t. What's the derivative of L by di by dt? What would that be? Wouldn't it just be L d squared IL by dt squared? It's the second derivative, right? It's the first derivative of the first derivative is the second derivative. Okay. What about that next term there? Yeah, di by dt. So I'd have R plus dIL by dt plus, what do I do with that guy? Yeah. I took the derivative, differentiated it. That's right there. Differentiated it, right? Yeah, this would just be IL over C, right? The derivative of an integral is whatever's under whatever the integrand is, right? I get that. Is that in my standard form? It's not. Trick question, right? It's close, right? The thing about my standard form is, and technically you don't need to get it into the standard form, but if you want to use any of those solutions that I wrote down, you're going to need to get it into the standard form because they all assumed that, right? I have a coefficient of 1 on that second derivative, right? This doesn't have a coefficient of 1. So how do I get to have a coefficient of 1? Divide both sides by L. So 0 divided by L is still 0. So d squared IL by dt squared plus R over L DIL by dt plus IL over LC. Okay. So that's my final differential equation. We'll write it here. So 0 equals d squared IL by dt squared plus R over L DIL by dt plus 1 over LC times just plain old IL. Okay, now comparing that to my standard form, right? Take that back. My standard form, I called the coefficient on the first derivative A, the coefficient on the 0 derivative, just the IL, is C, or sorry, B, and then it's all equal to C. So if I look at this thing, this is A, so A is equal to R over L. B is equal to 1 over LC, and C is equal to 0. Okay. Now, again, what I defined for myself over there, and so what I did here is and you'll see throughout this, I basically kind of defined all this in MATLAB the way that I would do this. And I got to figure out for myself, okay, well, I'll figure out the form of the solution. That's my second step, is to solve the differential equation and find the form of the solution. Okay. So to do that, what do I have to do? All right, so we found that A was equal to R over L, B was equal to 1 over LC, and we had a set of numbers for those. L is 0.1, okay. L is 0.1. R is 280. And C is equal to 0.4 microfarads. So it's 0.4 times 10 to the minus 6, right? Yeah. 0.4 times 10 to the minus 6. So to get the form of the solution from this, so when I say the form of the solution, what do I mean by that? What am I trying to find? Yeah, what's the transient? Specifically, what I'm trying to figure out is it underdamped? Is it critically damped? Is it overdamped? Right? So the key thing is I had this relationship where I said the roots of the characteristic equation were negative alpha plus minus the square root of, which order is it? Where is it? To go too far back. Alpha squared minus omega naught squared. Okay. Okay. So it's alpha squared minus omega naught squared. And it's always true that alpha equals A over 2 and omega naught is the square root of B. Okay. So, and what's that refer to? That always refers to when I'm looking at the differential equation, it's d squared IL by dt squared plus A times DIL by dt plus B times IL equals 0. Okay. I get that, right? So the key thing for me to figure out the form of the solution, what did I say? What's the key thing here to figure out the form of the solution? It's all rooted in what that alpha and omega are, right? So what am I concerned about? I'm concerned about whether alpha is bigger than omega naught or smaller than omega naught. I'm concerned about whether or not I'm taking the square root of a negative number or not. That's basically what it comes down to. So at this point, I got numbers. I know what L is, I know what R is, I know what C is. I calculate A and B, and then I use those to calculate alpha and omega naught, right? That's what I did here, right? This is the way that I entered this into MATLAB as an example, right? So I put in L, I put in C, I put in R, and then I put in my formulas for A and B, put in my formula for alpha, put in my formula for omega naught, and I get this result here. Okay. Now remember, the roots are negative alpha plus minus the square root of alpha squared minus omega naught squared. Okay. So this is what MATLAB spit out for me. Alpha is 1400 and omega naught is 5000. Okay. So is S going to be real numbers or is it going to be complex?
No, but
Complex. How do you know it's going to be complex? The square root is negative, right? I can see from this that alpha is less than omega naught. Alpha squared is going to be less than omega naught squared. Okay. And so this guy is going to be complex. So if I go back to my form of the solution, where is it? Here's my choices. Okay. Yeah, let's keep it here. Alpha less than omega naught, I get this right here. Right? It says that if I get a complex result, I have this formula. I have e to the negative alpha t. So alpha tells me how fast the amplitude is going to get smaller. Okay. And I have these decaying cosine and sine terms. And the frequency of these things is related to this whole ugly looking thing right here. All right. So what I'm going to do is I'm going to go back to where I was solving. I'm not going to worry too much about the math here. At this point, key thing for me is that I've figured out this guy's underdamped. And I'm going to say, I know he's underdamped. So I know that IL of t is equal to whatever the steady state value is, plus e to the negative alpha t times A1 cosine omega dt plus A2 sine omega dt. And let me make sure, again, I got to be consistent with what I wrote. Let me make sure. Yeah, it's consistent. All right. That's the right form. Now, I don't know enough to solve at this point. I know what omega d is. If I go back to those formulas, we're going to calculate them, and omega d is square root of omega naught squared minus alpha squared. So I could calculate all that stuff and that'd be good. I'm not too worried about that right now. Right? You guys see formulas, and so your brain goes to writing formulas. I see that. All right, don't worry about it. At this point, the key thing is what I know is that this thing is underdamped. Okay. I gotta go through the rest of my steps still. All right. Find the steady state values of IL and VC. So I don't technically need VC, but as practice, I want to get it anyway. Okay. So I want to figure out the steady state values. So steady state values means what do? I basically close the switch, right? If I'm talking about the steady state value, I'm long after t equal to 0, so the switch is closed. What do I do in this circuit? Short the inductor and open the capacitor. Exactly, right? So I have, I'll say IL of infinity, because it's basically this is the steady state current. The inductor shorted out. I have my R here. Capacitor is open. How much current flows in this circuit? None, right? Why none? Why 0? There's an open circuit. No current can flow through an open circuit. So I know right now that IL of infinity is 0. No current flows in this circuit in steady state. So what's the voltage here? What's that? 48. Yeah. A lot of times people start to say 0. It's good that you guys, if you guys are seeing that as 48, that's good. A lot of times people say 0 because, well, it's kind of unclear. But if I do a KVL, right, I say that if I did a KVL, I have the 48 volts, I have whatever the voltage drop is across the resistor, plus whatever this is. What's the voltage drop across the resistor? 0, because there's no current. I times R is 0, so that voltage and that voltage have to be the same by KVL. Okay. All right, so 48 volts, 0 amps. All right. Step 4 is easy. We already did this for ourselves, actually. I said, find VC 0 plus and IL of 0 plus. I gave you the numbers for these. I said this was 0.1, and I said that was 10 volts. All right. So I gave you that. No work I need to do here. Now I do have to do step 5 here, which is to figure out, analyze the circuit at t equals 0 plus to find dVC dt of 0 plus or dIL by dt of 0 plus. All right, this is going to be a little tricky for us. All right, so when I say 0 plus, what am I going to do with the switch? Close the switch. All right, now, what do we know about the inductor current at 0 minus and 0 plus?
The same.
They're the same, right? Now, the time period that we're talking about here is like nanoseconds, picoseconds. It's a very short period of time. We're saying that IL of 0 minus and IL of 0 plus are the same. Okay. Now, what I'm going to do then is I'm going to say near t equal to 0. It's not true always, but near t equal to 0, I want to simplify this circuit again. All right. What am I going to say about the inductor near t equal to 0? So in other words, from 0 minus, and I'll write it this way, from t equal to 0 minus to t equal to 0 plus. If that current stays at a fixed number, how could I think of that inductor? Not just as a wire in this case. So in steady state, we think of it as a wire, because basically at that point, the voltage across it's become equal to 0. In this case, not as just a wire, but as a current source. It has a fixed current that's equal to a particular value. In this particular case, that value happens to be 0.1 amps. And I've defined it to have the polarity that's drawn right there. So this guy, our circuit, is 48, 0.1 amps of current. I have my R. All right, and the voltage across there is VL. And in particular, I'm going to call this VL of 0 plus, because it's specifically the voltage across this thing right after the switch closes. Okay, now, what about talking about the capacitor? What do we know about the capacitor voltage from 0 minus and 0 plus? VC 0 minus and VC 0 plus. What do we know about those two? They're the same. And in this case, I was told they were 10 volts. So in the case of the inductor current, we said at 0 minus and 0 plus, they're the same. So over that short period of time, we thought of the inductor as a current source that had a fixed value. Over this short period of time, the capacitor holds a constant voltage. So how am I going to think of the capacitor? Voltage source, right? So over the short period of time, I'm going to say this guy is a 10 volt source, like so. All right. And I have that relationship. Now, what the heck is it I'm trying to do? I'm trying to find DIL by dt of 0 plus. How is that going to help me? Am I just being a nerd drawing funny circuits, making weird assumptions? There had to be a reason why I did this, right? What's the reason? Does anything in my circuit there relate to those derivatives? There is something that relates to those derivatives that I wrote here. Well, yeah, so the voltage on the inductor, V sub L, is DIL by dt, right? So if I solve for VL of 0 plus, VL of 0 plus is equal to 1 over L times DIL, or not 1 over L, sorry. VL of 0 plus is L times DIL of 0 plus by dt. So if I can solve for that voltage, I can solve for that derivative. And then I got everything I need to get the initial conditions. Okay, no, so how do I do that? So I had a 48 volt source. I had a 0.1 amp current source. This is VL of 0 plus. I don't know what that is, but I know this is a 0.1 amp current source. I have my resistor, and then I have 10 volts. So how should I solve for the voltage across that inductor? How should I solve for VL of 0 plus? KVL, right? So we got to be careful. Again, I'm going to do KVL the way I always do, which is to start in the bottom corner and go around clockwise, right? So 0 equals what? Negative 48 plus VL of 0 plus, right? Which is the thing I don't know, plus the voltage across that resistor. Now, what's the voltage across that resistor in this case? This is 280 ohms. What's the voltage across that resistor? Yep, 280 times 0.1, because I know the current through it. And then I know the voltage across the capacitor is 10 volts. So that tells me that VL of 0 plus is 48 minus 10 minus 28, whatever that works out to be. So what's that? 48 minus 28 is 20, right? Minus another 10 is 10 volts, like that, right? As long as I did my subtraction right. Okay. So that tells me then that DIL by dt of 0 plus would be equal to 10 volts divided by 0.1 henries, right? That's my L value. So that works out to be, I don't care about the units on this, but 10 divided by 0.1 is 100, right? And I would say this guy has units of amps per second because it's a derivative, right? I by dt, amps per second is what that guy has units of. Okay. I'm not too worried about the units. I'm more worried that you guys can follow through that process, but it's got amps per second. It's a rate of change of current, right? All right, so that was step 5. Step 6, which we probably don't have time for today, right? So I calculated it all here for myself, right? So this is how I calculate it. You guys can take a look at that once I upload this. But then step 6 is to figure out what the unknowns are. And that's what we're not going to have time for today, but that part's really not that hard, right? What I have right now is that IL of t is IL of infinity plus e to the negative alpha t a1 cosine omega dt plus a2 sine of omega dt, like that. All right, and I have a number for alpha. Have I written it out for myself here somewhere? I didn't write it out for myself. I probably should have. All right, I've got a number for alpha and I've got a number for omega d, right? Now, to be able to solve for the initial conditions, or to solve to get the full result, at this point in time, omega d I got a number for, alpha I got a number for, IL of infinity we said was 0, right? Because we said the steady state current was 0. What am I solving for at this point by the time we get to step 6? A1 and A2. All right, and so I have for myself already, this is where I would use these results here. I gave you these kind of general form to solve for. Where is it? For the underdamped case, I get these results. X of 0 is equal to the steady state value plus A1. The derivative at 0 is equal to that whole thing. So I basically get a set of equations with 2 unknowns, right? So I can just jump right to this. I mean, technically, yeah, I should take the derivative. What did I do? I took the derivative of the top thing, got that, plugged in t equals 0, and got these 2 results in both of them, right? You could do that, or I gave it to you. All right. So basically, what I'm left with here is this, right? And so I specifically have IL of 0, the value that we found for that, which was 0.1, is equal to IL of infinity, which is 0, plus A1. What's that tell me that A1 is right off the bat? 0.1, all right? Now, I also have that DIL by dt of 0 plus is equal to negative A1 alpha plus A2 times omega d. Okay. Now, it's 2 equations and 2 unknowns. I already know one of the unknowns, so I can just plug everything in here. We said this guy was equal to 100. I plug in my values of alpha and I plug in my omega d values. We're going to look at this at the beginning next time. All right, but what I am going to get with this ultimately is this result. At the very beginning next time I'll look at this, but let's just do a quick check, right? We said IL of infinity, the steady state value should be 0. We said that the initial condition should be 0.1. Well, I see my steady state value is 0. I see my initial condition is up there at 0.1. Okay. Now, maybe it looks like a little bit higher than that, but if you're looking closely, you actually see that it starts at 0.1 and actually goes up a little bit. All right. And then this is my underdamped response. So what I'm seeing is a cosine sine thing that is decaying over time. All right. So that's, again, we'll go through that a little bit more at the beginning next time and start doing some more examples. That's it.